So we're going to talk about rational functions now. Now, a rational function is a quotient of two polynomials. So just like a rational number is a number that can be written as a ratio, hence the word rational, right? Ratio of two integers. A rational function is basically can be written as a ratio of two polynomials. Now, one of the parent functions we've already explored is a rational function. So hopefully you sort of can think of this on your own, but that's going to be that reciprocal function. Why is that called rational? Well, we've got the constant function 1, that's a polynomial, a constant function can be a polynomial, divided by the linear function x. So this is a quotient of two polynomials. So our reciprocal function, remember, looks like this. Again, this is just a quick sketch. And what unique graphical features does it have? Well, it has a vertical asymptote. When we don't shift it around at all, it's at x equals 0. And it also has a horizontal asymptote, again, if we don't shift it around at all, at y equals 0. So, and what does the relationship have to do with the domain and the range, right? So the domain includes all of the values that where the function's defined, right? So anywhere except where you have this vertical asymptote. So the domain is going to be all real numbers except where there's an asymptote. And the range is going to be all real numbers except where there's an horizontal asymptote. So we move on to sort of summarizing in general how do we find the vertical and horizontal asymptotes of rational functions. So if you're given some rational function, n of x is the numerator polynomial, d of x is the denominator polynomial, right? So you think of this as being some big expanded polynomial over some big expanded polynomial. It doesn't always have to be this complicated, but at most it's this. So let's look at all the possibilities. So the graph of f is going to have vertical asymptotes at the zeros of d of x. So think about the reciprocal function f of x equals 1 over x. It had a vertical asymptote where x was 0, right? Because that's what makes the denominator 0. We can't divide by 0, right? So that's why we're going to get vertical asymptotes anytime we try to divide by 0 when the denominator has a 0. So everything that we just talked about previous to this topic about finding zeros of a polynomial, this becomes really crucial for rational functions trying to find the vertical asymptote. Then in terms of horizontal asymptotes, it's a little bit more involved. You have to look at the degrees of the numerator compared to the degree of the denominator. If the degree of the numerator, right, the numerator has degree n, is less than the degree of the denominator has degree m. So I'm going to write this in another way. So this is saying the degree of the numerator is less than the degree of the denominator, right? That's what we're saying. So the numerator is smaller than the denominator in terms of degree. Then, just like here, right, this was a constant that has degree 0 over a degree 1. So anytime that happens, including the reciprocal, then the line y equals 0 is going to be a horizontal asymptote. If the degrees are equal, then the graph will have a horizontal asymptote at the leading coefficient of the numerator divided by the leading coefficient of the denominator. So y equals that ratio. And if the degree of the numerator is larger than the degree of the denominator, then the graph has no horizontal asymptote. So we're going to have to talk more about that. Now, not mentioned in this box that I took from the book is that if n of x, the numerator, and the d of x, the denominator, have no common factors, then the zeros of the rational function will be the zeros of the numerator, right? So we talked about what happens for the zeros of the denominator, but what about the zeros of the numerator? So if you have a place where the numerator is 0 and you're dividing by some other number, 0 divided by that number will give us 0. So a 0 in the numerator polynomial will give us a 0 of the rational function. But also not mentioned is what if, so here I say if they have no common factors, but what happens if n of x and d of x have a common factor, right? Well, if they share a common factor, that means there's some value where the numerator is 0, but also simultaneously the denominator is 0. And this is an undefined expression, okay? So what that's going to usually lead to is a hole in the graph. Okay, we will explore this later in the course, but I just want to plant that seed now that 0 divided by 0 is not 0. Okay, so if the numerator is 0, but the denominator is not, then yes, that's a 0. But if the numerator and the denominator are both 0, we've got some sort of funny behavior happening. So let's look at a simple example. If we just think about transforming our parent function, the reciprocal function, by adding 2 inside the function, we know that's going to shift the graph left 2. And so what do we have for asymptotes? Well, we have a vertical asymptote at x for x equals -2, and horizontal is still y equals 0, right? So note that the degree of the numerator here is 0 because there are no x terms, right? It's just a constant. And the degree of the denominator is 1. So the degree of the denominator is larger than the degree of the numerator, which means, and this confirms, that the horizontal asymptote is at y equals 0. And also agreeing with above, where the denominator is 0 is where we get a vertical asymptote, right? So x plus 2 will give us a 0 when x equals -2.